Good afternoon, everyone. Thanks for joining our webinar this afternoon. I'm just going to give it another minute or so, let a few more people trickle in, and then we can get started. All right, got 1 minute past the hour by my watch, so let's go ahead and get started with the presentation we have for you guys here today. My name is Vinny Lamovic. I am the Ansys simulation specialist here at EAC Product Development Solutions. We will be recording this session today, so pending any technical difficulties, everyone's going to receive a recorded replay of this webinar. And following the session today, there's also going to be just a quick survey, like 4 or 5 questions. Shouldn't take you more than a minute or two that'll appear. So please stick around, just answer those. That's very helpful for us as we continue to broadcast these and send them out to our customers. As we wait for a few more people to jump on here, I'm going to start off with just some quick background of who EAC is and what it is that we do. So here at EAC, our company's mission is to transform the way that companies design, manufacture, connect to, and service their products. Now, some of you have worked with us for many years before this, have heard us say this at least once or twice, but some of you that are a little bit newer to us might be wondering, connecting all this stuff, transforming, what the heck does that mean? Well, it means that everything that we do is to help companies build better products is connected throughout our organization and yours. We don't like to see ourselves as just another value-added software reseller. We like to see ourselves as a highly trusted business consultant that's aligned with your business. Just look at all the areas that we're capable of providing support. We're Platinum PTC partners, preferred Ansys partners, and Formlabs 3D printing partners as well. On the engineering side, we also have a full staff of engineers that consist with product development, consulting, or any other questions that might arise as you are trying to get new designs out the door. We also have an implementation staff that is ready and able to come on site to ensure that your PLM launch is nothing short of successful. We are headquartered in Minneapolis, but we are spread throughout the country to ensure that we will always have someone local that you can count on in a pinch. Now, a little more about the Ansys side of things. Most of you probably think of simulation when you hear the word Ansys, and that is exactly what people at Ansys want to hear. They have put forth a great effort since they were founded in 1970 to do one thing and to be the best at it, and that thing is simulation. This is the only thing that they focus on, and it shows. Their customer support system is unrivaled with over 450 PhDs on staff in over 70 locations in 40 different countries. I've actually heard firsthand from some of their applications engineers that they enjoy getting difficult problems to solve because they love the challenge. So any problem you have as you're working in your day-to-day life, we would love to help you come up with a solution. Now, if you choose to focus on one thing, you better be the best at it. And Ansys' reputation absolutely backs them up here. They are 3 times larger than their nearest competitors, and 96 of the top 100 Fortune 500 industrial companies use Ansys. I always like to repeat that just to let it sink in. 96 of the top 100 Fortune 500 industrial companies use Ansys. And a huge reason for that is on the bottom half of this screen. Ansys is completely CAD agnostic, so it can really work with anyone. Doesn't matter if you're using Creo, SolidWorks, Autodesk, or CATIA. Our simulation software can work with any CAD platform without any bias. Now, I've been using the word simulation a lot, and some of you might be thinking, a great simulation, but what does that have to do with me? I can't use simulation. I'm here to tell you that you can. I work with companies that use Ansys from the first design sketch all the way up to production, and you'd be amazed what is possible by having a conversation with one of our applications engineers. Some of the things listed here help give an idea of how we can help. We work with things like autonomous vehicle companies all over the world, helping them reduce their validation time from 10,000 years down to 2 to 3 years with the simulations that they can run. And Ansys simulation results are even accepted by the FDA, FCA, and many ISO certifications that would normally require months to years of testing. And our recent partnership with Simutech here at EAC enables us to help you start tackling some of these complex problems and help our customers confront these issues during design, build the best possible parts in the shortest amount of time. So with that, I'm going to hand it over to one of our Simutech applications engineers. We have here with us Michael Schowalter. if you're out there, I am going to give you the ball and let you take over from here.
Okay, sounds good. All right. So as Vinny was saying, I work for Simitech Group. We're an Ansys technology channel partner. Much like what Vinny was talking about, we do some of the same things in different parts of the United States. So the motive behind all this is that we're trying to help people to do engineering, to do some simulation and innovate their products. And Simitech Group is the largest Ansys distributor in North America. And of course, we do sales, consulting, training in support of the Ansys products. So finite element analysis, Ansys mechanical, CFD products like Fluent that I'm going to be showing today. And we support their other software and simulation tools too. So world-class simulation from Simitech. We do mentoring, training, consulting services. We also do customer support. And we also have a portal that's called SimiTrain that has a lot of good content for training and tips and tricks type of material. We cover vast groups of different industries. Today we're going to be looking at aerospace specifically. And today we're going to be looking at fluids. Okay, so fluids, you can do all these different things with us with Fluent. Today we're going to be looking at external aerodynamics. And so just real quick, the Ansys tools, the multi-physics. Today I'm going to talk about fluids. Then tomorrow, Eric Alana is going to follow up with Ansys mechanical. He's going to take the pressure loads that I'm showing today on the drone, and he's going to show some deformation and some stresses. And then the next one, Andy is going to, my other colleague, he's going to show some electronics cooling on the third day. So today, out of all these products, simulation products, I'm going to focus on Fluent. There's a few supporting products that'll come up, Space Claim and CFD Post, but mostly I'm going to be focusing on Fluent today. So let's jump into it. I'm going to get out of this PowerPoint presentation. There it goes. Okay. Let me just shrink it down. There we go. Okay, so first when we start out, it's something called, I'll just pull it up here, it's something called Workbench, Ansys Workbench. And Ansys Workbench is kind of a palette where you can pull all kinds of different simulation tools. Here you see I've got Fluent pulled out here. So I did that by just basically grabbing a Fluent and dropping it on the Workbench. And it basically sets up my workflow for that one Fluent block. You can see this one, I say 20 meters per second, 10-degree angle of attack. AOA is angle of attack for the drone. So I could name this one something different. If I wanted to name it, maybe it's 20 degrees angle of attack. Then I could name this block something different, and I could set up my simulation block here to do that 20 degrees angle of attack instead of the 10-degree angle of attack. You can also pull in a static structural analysis, which Eric is going to go through tomorrow, but you link it to your fluid flow analysis. Then you can bring in the pressures from certain faces or certain walls within my fluid flow simulation, and you can import that and map that and interpolate it onto a structural analysis model. And so Eric's going to show that tomorrow. But today we're going to focus on the fluids part of it. So first I'm going to show you what the model looks like. Here we go. So what we're going to be looking at today is a drone. And you can see that this drone is, it's about 2 feet long. So it's a small radio controlled kind of drone. And it has a payload area in here that you can lift this up, and it has some kind of a payload. It has a camera on the front end, so you can see it's got a dome here and has a camera there. It's got 3 landing gear, 3 wheels. It's got the horizontal elevator and 2 vertical stabilizers, and then the support beams that go out to hold that in place. And it's got a push propeller. and of course the little electric engine in here and some electronics inside of there. And Andy's going to focus on the electronics and the heat that they cause and looking at and analyzing what that heat looks like. Well, the first step in doing any kind of analysis is that you have to have a solid model. So we do have a solid model. What we notice is that there's some symmetry. If I turn on this plane, if we look right down the middle of it, you can see that it's got symmetry right and left. And so if it does have symmetry, what you want to do is only maybe model 1/2 of it. You really don't want to model both sides of it. So today we're going to look at just 1/2 of it. The first thing I have to do is I have to model the air, not just the solid model itself. For the structural analysis, you do want all the solid parts. For fluids analysis, you want the stuff that's not there. So that's the first thing that I had to go and create. So I'm going to pull that up here. Basically, I wanted to create a wind tunnel. So I took my solid model and I created a big air volume. And I cut my model in half. So you can see that looking straight down the middle of it, I only have 1/2 of it. So I just have 1/2 the fuselage. I've got half of this front landing gear, the other landing gear, and the back elevator and vertical stabilizer. You want to get, if you're doing external aerodynamics, you want to get some certain distance away from it with the outside of your enclosure. So I have it, a little more than one wing, half a wing away. Probably it's a wing and a half away out to the enclosure here and to the top, so that I have some space for the free stream air to flow past it without getting disturbed and without hitting my outlet boundary. But I also want to have some little distance in front of it, as you can see here. So I have some clearance in front of it where I'm going to have the air coming in and not get disturbed by the aircraft too close to that inlet boundary. So you want to have some distance to the inlet. And you also want to have some area for a wake behind it. So I have probably about 5 aircraft lengths behind it where I can look at the wake and see what the wake looks like behind the aircraft. Okay, so this was the geometry, and this was in what's called space claim. That comes with Ansys Mechanical, it comes with Ansys Fluent, and it's part of your pre-processor. This is where you would import a CAD model, and in this case, what I did was extract an air volume, form an air volume or a wind tunnel around it. The next thing that you want to do is, you can see geometry. The next thing in my list is mesh. Okay, so I'm going to pull up what's called Ansys Workbench Meshing. This is the same mesher that's used for both Ansys Mechanical and for CFD products, Ansys Fluent. And so what I've got here is my wind tunnel. And if I zoom in, you can see that now I've got a computational mesh created on it. And this is a mesh. When you first come into Workbench Meshing, you have to choose what kind of physics you're going to use. So here, instead of Ansys Mechanical, I'm using CFD, and I'm picking Fluent as my CFD solver. And then you can pick some different kinds of information in here for creating the size of the mesh. You can also name things inside of here. I wanted to have this wall that is a symmetry wall. I wanted to name it so that when I get into Fluent, I can identify that wall and know that's my wall of symmetry. I also wanted to, let's get the walls of the drone itself. I also wanted to identify the fuselage. So these are the walls of the drone, and then the walls of the wing. You can see that they'll highlight on the inside of it. But basically, I'm going to be passing those pressures from that wing, so I wanted to identify that surface also. Then my inlet is going to be down at this end, and my outlet is going to be at the opposite end, down there. Okay, and now when I started meshing, I decided to choose something that's called cut cell meshing. All right, and I'm going to just pull up the mesh here, and it'll take a moment. Cut cell meshing is a polyhedral type of mesh that's basically going to be brick elements. They're going to be squares. And then when it gets closer to the surface of my drone, you can see that it cuts it basically. So this one mesh block right here, that face gets cut into actually 4 different smaller blocks. And as I get closer, this mesh cell gets cut into 4 blocks. So you cut, that's why it's called cut cell meshing. So it can quickly go from a very coarse mesh out here in the free stream to a very fine mesh down here along the body where I'm going to have gradients. I'm going to have gradients of velocity that go from free stream velocity down to 0 on the walls because these are no slip walls. And I'm also going to have gradients of pressure. And so I need to capture those. So as I zoom in closer and closer to the nose cone of this drone, when I finally get down close to the surface, you can see that I have 7 cells here, or 7 elements, as Ansys would call them, but cells, computational cells. I have 7 cells that are going to form basically what's called a boundary layer mesh. Okay, these are going to be extruded from the surface, so you can see what the inside of my drone looks like. Some of them are triangles, some of them are squares. They're extruded out, and basically they're going to be an extruded triangle or an extruded square, and they're going to form that surface. And it's with the cut cell meshing, it basically tries to form these and grow these normal to the surface as much as possible. When you go around a corner, of course, you're going to get something that's got a little angle to it, but basically they're like prisms. They're either triangles or they're squares that are they're rectangular, flat rectangular elements, or if they're triangles, they're prisms. So that's going to try to resolve that gradient. The first law of first commandment of fluid dynamics is resolve thy gradients. So wherever you have steep gradients of velocity, if you go from free stream to 0 velocity, you're going to need to capture that. And so that's what this boundary layer mesh is here to do. So I put in some size functions in there that you can see. I also have those same size functions on the rear portion. So here's the flap in the back, that's a control surface. And then the elevator, the horizontal elevator that's on there. I also have the same thing on the vertical stabilizers. And let's look at the statistics real quick. So this ended up being a mesh. You can see it's very uniform out in the free stream because I really don't have many gradients that are going to be there. I'm not going to have gradients of velocity or pressure. It's going to be all pretty uniform for the most part. So I have on the order of 8.2 million elements, total elements. And this is, of course, a half model. So that's kind of a quick overview of what the mesh looks like. The next part of it is the setup. So I'm going to pull up Fluent here. And in here, this is where you would specify your boundary conditions. So once again, you can see this is a Fluent window, and you can see that I once again have my wind tunnel in here, and it's color-coded by some of the different boundaries once you get into Fluent. Fluent recognizes the name inlet, it recognizes the name symmetry, and it recognizes the name outlet. So basically my inlet is actually this wall, but I'm also making these other walls that you can see over here. I'm also making those inlets. The arrows are pointing which way this boundary is. It's an inlet, so it's basically going in. Yellow is symmetry, and red is going to be an outlet boundary. So I basically have the top, this backside and the bottom, and this upstream end as inlet boundaries, and then finally I have an outlet boundary on the other end. So visually you can see what's going on with Fluent. You can also use the top, there it goes. You can also use this top ribbon to go through and set up your model. So the first thing you want to do is you want to check, this is called perform a mesh check. You want to make sure that you don't have any negative volumes in your mesh, or that you don't have any really bad aspect ratios of your mesh, that they're not long and skinny, or if they're tetrahedrons, that they're not like a little sliver. So that will give you a check of your mesh. Then you can check the quality of your mesh. We're not going to do that because I know it's already good. Here you can also see that you can pick whether you're going to use the pressure-based solver or the density-based solver. This is a low-speed drone. We're only going to be flowing at about 20 meters per second coming in. That's 40 something miles per hour. So it's not It's not highly compressible flow. It's not like it's a Mach 1 or Mach 2 or Mach 3. If you were doing high-speed external aerodynamics, you would want to pick the density-based solver in Fluent, and that's for highly compressible flow. And that's going to resolve shock waves a lot better. We're not going to have any shock waves, so pressure-based, steady state is good. We don't have to really worry about gravity because there's no buoyancy in this model. And the next thing we want to do is we want to look at some of the physics. So you can either go with the ribbon up here, or you can open up on the left side here in this outline tree. You can also look at all the different potential physics there. We're not doing multi-phase, we just have air. We are going to do turbulence. So we do have the turbulence model turned on, and I'll pop up the turbulence window. So it's you can run laminar. You can also run inviscid if you really do have high speed flows and the boundary layer is not a big issue. But for this one, we are going to have a boundary layer, and we are doing external aerodynamics, and so K omega SST is going to be the model of choice. And I believe now it's the default turbulence model in Fluent, so this will probably be turned on when you open up Fluent anyway. I haven't changed anything else. I'm using all the default settings for the K omega SST model. I'm not doing any of the other physics that you can see here, but as you can see, there's a lot of rich amount of physics in here. Okay, so that's the physics part of it. Next is the materials, and in Fluent, there's a good database of materials. Air is the default material, but if you did want to pick some other materials, you could pull up the fluids database, and you can just scroll through it, and you can see there's a lot of different gases and liquids in here. All the way, if we scroll all the way down, you can see water vapor, water liquid, a lot of different things for combustion, for chemical reactions, a lot of that stuff in here. So you can grab those and use those if you're doing something other than just air. Here, I also I turned on the ideal gas equation. You can have density as a constant, but because we were a little bit of compressibility in there at 20 meters per second, I thought I would turn on the ideal gas equation so that density is not a constant, but it uses the ideal gas law. So we can have a little bit of compressibility. The next thing down here, cell zones, we only have one. It's my enclosure, my wind tunnel. Because those are just walls, it's not another, I don't have anything else except my air volume. And these are just walls that are hollowed out of it that form the outside surfaces of the drone. Next is boundary conditions. And I'm gonna double click on this word, boundary conditions, so we can see them over here. And if I click on the word inlet, you can see that it's set up as a velocity inlet. And I'm gonna edit this box so we can see it pulled up. So in here, you can pick what velocity you want the inlet to be. In this case, I'm using SI units, so I picked 20 meters per second. And what's important too is that you can also pick what directions it's flowing in at. In this case, this was, you can see up here in my description, this is a 10-degree angle of attack. So I actually picked, instead of having the inlet be normal to the boundary, actually picked Cartesian coordinates. And here, down here, you put in a unit vector. And so in my model over here, you can see here's my X, Y, and Z directions. So we can see that Y is in the upward direction, X, negative X is the way that the air is going to be flowing in. So, and I want the air to flow up at 10 degrees. So I want it to have a little Y component. And so if you calculate the components, do the sine, cosine of 10 degrees, you'll see that this is the unit vector for an angle of 10 degrees angled upward from that inlet. So I'm going in the negative direction, so I give my unit vector negative direction in the X, and positive, I'm going in the positive Y direction. So that gives me a 10-degree angle. Thermal, I'm doing isothermal, so everything is at kind of ambient 300 degrees Kelvin, 27 degrees Celsius, so we're not doing anything fancy there. The only other thing, the symmetry boundary, there's nothing to do with the symmetry boundary. We'll click on the outlet, but here I'm just basically picking a 0 gauge pressure, which is atmospheric pressure. So nothing fancy there either. Then the next thing you would do is you'd come down, you would initialize it. So when you double click on this, I picked just my inlet boundary conditions and basically initialized it. And then you would click on run calculation. You'd put in, who knows, maybe 200 iterations. You'd click on calculate, and then you would let it run and see if you converge on a solution, which I did. I'm not going to actually run it right now, but we're going to go next. And after we have a solution, we're going to pull up the results. So I'm going to pull up the results. Here we go. And what it first looks like is this. It really doesn't have anything in there. It's basically just a wireframe when it comes into the CFD post, which is the post processor. And I could turn on walls of my drone. Here's what the outside walls look like. Here's the walls of the wing. So I can make them gray so I can see where the surface of my actual vehicle is. And of course, it's still half symmetry. So it kind of looks like that. One of the first things I might want to do is that I might want to release streamlines from the inlet. And I've done that already. So I'm going to show you what it looks like. And I did it on a plane. I actually put in a plane here. This is plane 1. It's really easy to create a plane. You just go in here in location, you say a plane. I'm going to call this an XY plane, and I'm going to move this so that we can just see where this plane shows up. Shows up over there. I could move it if I didn't like where that spot was. I could move it farther over to the right, or to the left, I'm sorry. If I want it over this other way, I could move it over that way. So you can easily put in a plane, and then on that plane, that's where I put my streamlines. So if I double click on streamlines, you can see you can pick 3D streamlines or surface streamlines. So here I've got surface streamlines. And if I turn this sideways, you can see that they're coming in at a 10-degree angle. So if I rotate this a little bit until I get them coming in just about parallel, and I'm going to zoom in on it. So you can see my free stream down here is just about coming in parallel, because really, even though I am angling my inlet velocity, really it's the aircraft in normal conditions that's moving. And so you would be pitching up at 10 degrees to have a 10-degree angle of attack. So I just rotated my whole domain so that I could have the streamlines coming in at about parallel. So this is what it would look like if the nose pitched up 10 degrees and you're flying with a 10-degree angle of attack. I'm going to zoom in here and I'm going to add in vectors that I also added on this same plane. And I'm going to turn off my gray here for the wing so that we can kind of see what's going on here. And let me turn off that on the drone too. Okay, so basically we're looking at that plane and air is coming up, it's hitting the wing. You can see I get a stagnation point here where these velocity vectors basically go down to 0. Here's my scale for speed, and my streamlines and velocity vectors, they quickly go over the top of it. This is where I'm getting my highest velocity, and this is where I would expect to get some of my lowest pressures, right where the velocity goes the highest. And that would give me lift because I'd have higher pressure on the bottom of the wing, lower pressure on the top. And then at the exit of it, you can see that you get somewhat of a separation here. It's not quite a recirculation zone, but you do get some separation here at the trailing edge of the airfoil. Okay, I'm going to turn these streamlines off real quick, and I'm going to show you pressure. And this is pressure on the wing itself. And it's taking a second before I can move it. Frozen there. There it goes. Okay. Yeah, so here's the pressure on the wing. And just like we were talking about, you would expect where the velocities are the highest. As we were looking at those streamlines and vectors, you would expect that to be my lowest pressures. You would expect the stagnation area on the wing to be my highest pressures. So you can see the stagnation is, since it's coming in at 10-degree angle of attack, my stagnation area is down here towards the bottom and not on the center of the wing, but more towards the bottom. That's where I get the highest pressures. I get the lowest pressures on the top, get the highest pressures on the bottom. So that's going to give me some lift. This is the information that I gave to Eric, and Eric tomorrow is going to show you this mapped onto his Ansys mechanical model, and he's gonna then show you some deformation and stress of the wing based upon those pressure loads, and maybe make some changes to it to be able to better handle those pressure loads and not deform quite as much. Finally, I wanted to show, okay, so this was 10-degree angle of attack. I also had pulled up a level flight. So you can see what a level flight looks like and the streamlines, what those look like. So you don't get as much speed up at the top, so you don't get as much lift with it as you do with that 10-degree angle of attack. Then I also have 20-degree angle of attack pulled up. And here you can see that you get a big separation of air as it goes over the top of the wing. Now the nose is pitched up quite a bit on my drone. I'm at a 20-degree angle of attack. And here you get a big recirculation back here. You also start getting into a dangerous zone of maybe you're going to get so much drag and not so much lift that you're going to have a stall. You don't want a stall to occur, but that's what's beginning to look like it's going to happen. Basically, I ran this at different angles of attack, and I calculated the lift on the wings, and I calculated the drag. Lift is basically in the Y direction. Drag is going to be in the X direction, and looked at these two curves. So basically, this is lift in my orange curve, and this is drag. And I did it at a negative 5 degrees, so nose pitch down 5 degrees, at 0, level flight, 5, 10, 15, 20 degrees angle of attack. And at 10 degrees angle of attack, this is where I'm getting the highest lift to drag ratio. Once I start getting to 20, I'm losing some lift, and I'm getting in a dangerous zone where I may have a stall that would occur. So basically, you can use Fluent to, let me show you the workbench real quick. This was my workbench running the level flight, 5 degree, 10, 15, 20, and negative 5 degrees. You can basically go in, once you've run one of these, you can basically duplicate this block. It'll create a whole new block here. Then I can come in, I can rename it and say, hey, maybe this is going to be 30-degree angle of attack with pitching the nose up, but it's going to make this whole block in here. It'll take a little bit of time, but it's going to make the whole block, and then I can go in, I can edit my setup. I don't have to change the mesh, I don't have to change the geometry, but basically I'm going to change the angle of how my inlet air is going to come in, and I'm going to change it from this one was negative 5 degrees, maybe I'm going to change it to 30 degrees, pitch the nose up. So I'm going to go into Fluent like we saw before, and I'm going to change, let me pull up Fluent one more time. I got the license tied up there real quick. But basically I would go back into Fluent and I would change that unit vector on my inlet boundary so that now I'm going to do the cosine and cosine of 30 degrees. I'm going to figure out what those unit vectors are for X and Y. I'm going to change those, edit those. I'm going to put those into Fluent. I'm going to rerun it, and I'll have a new block here that's going to give me the results in Workbench. And then basically I can save my Workbench at the end of this, and I will have saved all of my solutions that I've put in here on this Workbench. So it's a really good place for organizing your project. And I think that's about it, Vinny. Maybe we could open it up for questions now.
Yeah, sure. I don't see anything in the queue at the moment, or nobody has raised their hand. So I guess with that, I would just, I don't see any questions, but.
Well, did you have any questions, Vinny? Just out of curiosity. I know I'm putting you on the spot, but just curious.
Well, I guess the question that I kind of can, but I guess I would say what would I do if, say, I wanted to follow up with you guys and learn more? So to that, I would say you could follow up with either myself or Michael. I can just, there we go. Have both of our contact information right there. So just to wrap things for today, a short survey that will appear after we end. If you, like I said, if you got a couple of minutes, really appreciate it. Stick around, answer them for us. The feedback's helpful for planning these in the future. If you liked what you saw today and want to learn more, we will be hosting another webinar tomorrow where we'll be showing you how you can save time and money in simulation with fast access to materials data if you might need it. If there are any projects that you're working on where material properties are important to you, feel free to reach out for more information about that. But any additional questions or comments, don't hesitate to reach out to either Michael or myself with this contact information here. That's all I have, Michael, unless you had anything that you'd like to add. Thanks again to everyone for attending, and have a great rest of your day.
Yeah, that's it for me also, Vinny. Thanks a lot.